knowledge base systems. So let's first talk about building a knowledge base. It's the same as propositional logic, but the sentences are now in first order logic. So before, if it were things like yellow light, now we have or something. When it comes to doing inference in first order logic, we could either convert everything into propositional logic and then do inference in propositional logic, or we can do direct inference within first order logic. Let's first look at converting to propositional logic. The goal is pretty clear. We're trying to convert sentences in first order logic to sentences in propositional logic, and once that's done, we can just use logical inference in propositional logic, which we know how to do. But there are some complications, right? Like, how do you deal with variables? Converting sentences consisting of constants, that's fine, but how do you deal with variables? Because there's no such thing as variable in propositional logic. So let's look at universal quantifiers first. How do you get rid of it? So suppose we have a sentence that says, for all x, king x and greedy x implies evil x. Okay, given this sentence, can we infer that King John and greedy John implies evil John? Yes, because that must be true for all x, so it should work for any constant. So, to remove universal quantifiers, we generate sentences by plugging in all ground terms, like non-variable terms, so constants and then functions of constants. So you end up with a lot more sentences. I mean, that's what we get for going from first order logic, which is more expressive, to propositional logic, which is not as expressive. How about existential quantifiers? Suppose we have a sentence, there exists x such that king x and greedy x. So there is some x who's a king and also greedy. Can you infer that King John and greedy John? Not really. I mean, we know there is some x, but we don't know which x it is, or which x's it is. So, in order to deal with existential quantifiers, we use what's called Skolomization. And here's how it works. We use what's called Skolem constant in place of the variable. So we are introducing a new constant. So John is a person and there's a pet and John loves that pet. So there is some x for which this is true. So we just give that x a name, C. So the sentence just becomes person John and pet C and loves John C. So what if we have a mixture of universal and existential quantifiers? So say we take the same sentence, but replace John with a universally quantified variable y. And if we take the same approach as before and simply replace x with the Skolem constant c, then we end up with a sentence that is not the same, because the original sentence says every person has some pet that they love, and the pet that each person likes could be a different pet. But the sentence we have now is every person likes the same pet, C, which is not true. So we use Skolem function instead and pass in the universally quantified variable as an argument. So instead of C, we have C of y. Now this is fine, because now each person can have their own pet that they love. And if you have more than one universally quantified variable, then you use all of those as arguments for the Skolem function. Then how do you do inference in first order logic? The question is, how do you deal with variables? For example, let's say we have a sentence that says every king is evil. So for all x, king x implies evil x. And suppose we also know that John is king. Can you infer that John is evil? You can, right? Because every king is evil, and since John is king, then John must be evil. So the idea is to somehow substitute the variables with constants. So here's how substitution works. You first have to specify which variables are being substituted with which constants or variables in which sentence. So for example, when you say X will be substituted to John and you want to do that substitution in this sentence, then the result is this. So take the same sentence, but every time you see X, you replace that with John. And if you take the same sentence, but this time substitute X with Richard, then you would get this sentence. So you remember how modus ponens works, right? So we take alpha, and alpha implies beta. You conclude that beta is true. Or we could have a slightly more complicated expression where we have P1, some proposition 1, P2, and we know that P1 and P2 implies Q, then we can conclude that Q is true. But in this case, we have an issue because the propositions don't match up. And they only match up using some substitution theta. And that substitution is some substitution that makes propositions pi prime and pi equivalent. Once you have such theta, then the resulting Q becomes Q with all the substitution made based on theta. So here's an example. So we have P1 prime is King John. And then P2 prime is greedy Y. And then we have an implication from P1, P2 to Q. So we have King X and greedy X implies evil X. We can't use modus ponens right away because these don't match up with these. So we need the substitution theta that will match those up. And in this case, it's this substitution. So we're going to change every X to John and every Y to John. Then these two will match up. So once you do this modus ponens, then the result you get is take Q, but do the same substitution. So if you apply theta to evil X, then you replace X with John. So you end up with evil John. This is how you do modus ponens, and same principle applies to modus tollens and elimination. And you can do forward and backward chaining as you did in propositional logic. Okay, how about resolution? Again, the way resolution works is you keep applying resolution rule to pairs of sentences where in one sentence you have some atomic sentence, say E, and the other sentence you have the negation of that atomic sentence, not E. And then when you resolve these two sentences, complex sentences, then you get a new sentence without E. And you keep reducing it until you find nil. In first order logic, you run into the same issue that we just dealt with, which is two sentences may not be the same unless you do some substitution. So we call this unification. So we're trying to make sentences match using substitution. For example, suppose we have two sentences, knows John X and knows John J. Which substitution would make these sentences equivalent? Well, the substitution we need is taking John and changing it to Jane. And this substitution is called a unifier of these two sentences. Here's another example. Knows John X, knows Y Bill. Well, in this case, we would want to substitute Bill in place of X and John in place of Y. Okay, again, this is a unifier of these two sentences. Okay, how about knows John X, knows X Bill? Assuming that these are two separate independent sentences, these X actually do not necessarily mean the same object. So we first do what's called standardizing. Which means to rename the variables so that the sentences don't use the same variable. So this becomes knows John X, and then knows Y Bill. And then we can unify. So again, the same substitution will be suitable. Given the sentence knows John X and knows Y, mother Y, which of the following unifies those sentences? Well, A obviously works, and B obviously doesn't work. The question is C. The thing about substitution is that all the substitutions happen at the same time. So if you apply C to these two sentences, then you get knows John, mother Y, and then knows John, mother John. So the sentences are not the same. So the answer is A. In some cases, you have multiple unifiers that can unify the given pair of sentences. In such case, you want to choose the most general unifier, which is a unifier that's the least restricting. So in this example, one unifier that works would be setting X to some random name, say Bill, Y to John, and then Z to Bill. Okay, this works. This is a unifier, but it's overly restrictive. A better one, a more general unifier, would be setting X to, say, Z, and then Y to John. So this is the most general unifier. So before we can use resolution in first order logic, the first thing that we need to do is unification. And the second thing we need to do is to convert first order logic to CNF. And it requires quite a bit of steps, as you can see here. So we first have to eliminate implication, and then remove quantifiers, which takes multiple steps, and then distribute AND over OR. Let's look at this with an example. So we have a sentence that says, for all X, for all Y, animal Y implies loves XY. That whole thing implies there exists Y such that loves YX. So for all X, if X loves all animals, then there exists an animal that loves X back, I guess. Okay, so how do we change this to CNF? The first thing we do is to eliminate implications. So again, when you have P implies Q, we can convert that to not P or Q. So here is our first implication that we need to convert. This is P, this is Q. So we have not animal Y or loves XY. And then still the same universal quantifier. This whole thing is a P, and this thing is a Q. So we put a not around that, or there's just a Y loves YX. And then we have a universally quantified X surrounding everything. Okay, so we're done with the first step. And then second step is we want to remove quantifiers. Before we can remove quantifiers, we have to do two things. One, we want to make sure no negation is outside a quantifier. And two, we want to standardize variables. So in this example, this negation is outside of this quantifier. So we want to move that negation in using De Morgan's law. And when you use De Morgan's law, universal quantifiers become existential quantifier and vice versa. So we have for all X, there exists Y, not animal Y, or loves XY, or there exists Y, loves YX. Now we have to standardize variables. And note that we have two Y's in this sentence, but those two Y's are not the same Y's. So let's change the second Y to a different variable, say Z. So we have for all x, there exists a y, and we might as well distribute the negation. So this becomes animal y and not loves xy, or there exists a z loves zx. Now we're ready to eliminate quantifiers. To remove existential quantifiers, we have to scholemize. In this case, we have a universal quantifier x surrounding everything. So instead of using Skolem constant, we have to use Skolem function. So for all x, animal c of x and not loves x and c of x, or loves some other Skolem function, say d, again of x, then x. So we got rid of all existential quantifiers, and now how do we get rid of universal quantifiers? We just drop the quantifier. So we have animal cx and not loves x or loves dx x. And lastly, we want the sentence to be conjunction of disjunctions, so we have to distribute and over or, which gives us animal cx or loves dx x and not loves x cx or loves dx x. So let's look at an example of doing resolution in first order logic. So suppose we're trying to prove Tweety is a bird, and in our knowledge base we know that for all x, feathers x implies bird x, and then we know that Tweety has feathers. So the first thing we need to do is to convert everything to CNF. So it's just not feathers or bird. And the second sentence in the knowledge base is already in CNF. So let's number them again, 1, 2, and then we add the negation of what we're trying to prove. Bird. And we start resolving, and hopefully we'll get to a nil. So I want to resolve 1 and 3, and we need to use substitution. So I'm going to use the substitution in which x is replaced with Tweety. Then I'm left with not feathers Tweety. And then I resolve 2 and 4, which gives me nil. So we're done. So therefore, bird Tweety. Let's look at a more complicated example. So we first need to convert these to first order logic. For example, Jack owns a dog would be, there exists an x such that x is a dog and Jack owns x. And you can do this for all the sentences. Okay, is this what you got? Good. And then we have to convert this to conjunctive normal form. So the first one's easy, right? So we just have Skolem constant, dog, say D, and owns Jack D. And you do that for everything else. And is this what you got? Good. These are all n's. And now we can start resolving. Okay, so I laid it out for you. I want you to find a mistake in this proof by resolution. A, B, C, D, or E. So D is the correct answer, where this thing should have been negated. And you can approach proof by resolution as a search problem, where each state consists of all the sentences in the knowledge base, and your initial state is the original knowledge base with the negated Q, the thing you're trying to prove. And the successor function is taking any two sentences and resolving them and adding the resulting rule to the knowledge base. And your goal test is checking whether the knowledge base contains nil. There's a logic programming language called Prolog, and there depth first search is used.